This is the last part of chapter 20, and this is on nitriles. And the first thing we're going to do is talk about the nomenclature. So, interestingly, IUPAC has two different ways that they use depending on how big the molecule is or how much other things are in there. And so if it's a simple molecule where the only functional group is the nitrile, then they'll just stick the word nitrile onto the end of the alkane of that number of carbons. And then they would consider the nitrile carbon to be carbon number 1. And if you have a more complicated molecule, then or even just a larger molecule, then what they do is they treat it like a carboxylic acid derivative, which, as I've said, it really is. And so they name it like a carboxylic acid, but instead of putting oic acid at the end of the word, they drop the ic acid, but they keep the O. And so then you have the word O-nitrile at the end of the carboxylic acid name. So it helps if we look at a few examples. So in this case, remember that this is truly a carboxylic acid derivative. This carbon of the nitrile is in the same oxidation state as the carbon in carboxylic acids. And so it's carbon number 1, so the chain is numbered accordingly. And so everything else falls where it may. And so this is a fairly simple molecule. And so they named it just like an alkane, and then they just stick the word nitrile on it. And you could also use the other style I was talking about, which is to treat it like a carboxylic acid. So if that were an acid group there, it would have been 4-methylpentanoic acid. So because that acid group has been turned into a nitrile, then we put the O, keep the O, and then just put the word nitrile after that. And this kind of style works no matter what. You can always treat it as a carboxylic acid derivative, and the nice thing about that is then you always know which carbon is number 1. Here's another example. Again, this one has to be number 1, so you number accordingly, and you get either 4-methyl-3-pentene nitrile or 4-methyl-3-pentenonitrile, and they really mean the same thing, and the only difference is whether you have that O or that E inside the word there. Sometimes you'll see a little bit more complicated molecules, and then it's not so obvious, and so using the acid style of nomenclature is better. So again, we're still treating this as carbon number 1, and so we number the chain this way. Then we have this ethyl group at carbon number 2, and this guy at number 4, and the phenyl group, the benzene ring, at number 5, and so you come up with this kind of a name, and that is a little easier. It's obviously named as a carboxylic acid derivative in that case. The other thing that's kind of interesting is the nitrile common nomenclature. There's also a couple of ways to do those, and so one of the things that is done is to use the term nitrile and treat it like an acid and drop the ic acid. And in the older style of naming acids, like say acetic acid, they might actually have to put an O in there. And then there's other, even older literature referring to these groups as cyano groups. So both of those old styles of nomenclature are still out there for certain molecules. And the reason that organic chemists stopped using the term cyano and calling these things cyanides and started using the term nitrile is because of the biological significance of cyanide ion as a chemical toxin. And these molecules, these organic nitriles, are not toxic in the same way because the bonds are covalent, and cyanide ion is an ionic ligand in the bloodstream. It binds very strongly to hemoglobin and causes chemical asphyxiation. Well, your covalently bound cyanide groups or nitrile groups don't behave that way, and also they're not particularly water soluble. So there are good reasons not to get your organic molecules tangled up with something that's really an inorganic phenomenon. So that's why they moved away from calling these things cyanides. So here are some more examples using both common and IUPAC names. I mentioned acetic acid is the 2-carbon acid, so this guy is still derived from the 2-carbon acid, so the common name for that is acetonitrile, or the even older style nomenclature would have been methyl cyanide. In the newer IUPAC, they would use ethane for the 2-carbon molecule, so ethane or ethanonitrile. This molecule is derived from acrylic acid, which was one of the acid names that you learned earlier in this chapter. And so the common name for that is acrylonitrile. And of course in IUPAC it's 2-propanonitrile. And remember, benzoic acid would have been the common name for the benzene with the carboxylic acid group on it, so the common name for that is benzonitrile. And IUPAC accepts that, kind of the same thing when we were talking about benzoic acid is really a common name, but IUPAC concedes that that's a very useful and shorter name. And remember, the whole thing about nomenclature is it's very clear what we mean when we say that. So benzonitrile is what most people call this. And if you wanted to know how IUPAC would deal with it in a more systematic way, remember it would have been benzene carboxylic acid, and so they drop most of that acid word and put in nitrile, so it's benzene carbonitrile is the real 100% IUPAC name for that. And here again we have a situation where we have a carboxylic acid and we also have a nitrile group. And so the carboxylic acid is the parent, and a nitrile is one example of a derivative of a carboxylic acid. And so the parent is going to take priority. So it has to be carbon number 1. And we can just treat this as a group then. And so if you need a group name, then we use the cyano for that. And so then you number accordingly, and you get that this is 3-cyano-5-methylhexanoic acid. So we're going to review how to make nitriles. I've talked about this a little bit in class. We know from chapter 11 that we can do SN2 reactions, and in that chapter there was a table that had a bunch of possible nucleophiles, and the cyanide ion was an example. And of course, not only is this kind of preparation limited to the kinds of things that work for SN2 reactions, also they're going to work pretty well because the cyanide ion is very small, and you're going to make a new carbon-carbon bond, and so it's actually a very good nucleophile. So here's an example. You just have to have preferably a primary or a not too crowded carbon attached to a leaving group and your substrate. And so this is the substrate, and cyanide ion is the nucleophile, and you get a substitution reaction to make nitriles. And in chapter 19 we talked about cyanohydrin formation, and if you needed to make a carbon that was tertiary attached to the nitrile, that would probably be a better route because of the limitations that you have to deal with on these SN2 reactions. So here's an example of where we're going to end up with a tertiary carbon. So if we have a ketone and we put HCN in there, we can end up with adding this carbon, and of course we're also adding the hydrogen, so that's how we made these alpha hydroxy cyano compounds. But anyway, we've got a too crowded of a carbon here to have done, or it's more likely to have been too crowded to have done the SN2 reaction. So this gives us an alternative to that, and of course if you don't want the OH, then there are ways to get rid of that. So I'm going to talk about something that we have not seen before, and that is the preparation of nitriles by dehydration of a primary amide. And I said that the nitrile is a derivative of a carboxylic acid, and one of the things that you'll start hearing a lot in the context of chapter 21 is we're interested in, can we make carboxylic acid derivatives directly from carboxylic acids? And it turns out that it's not really feasible to make a nitrile directly from a carboxylic acid, but it is okay and pretty easy to make a nitrile from a different carboxylic acid derivative. And a primary amide is a carboxylic acid derivative also. And so we can change one nitrogen containing carboxylic acid derivative, that is an amide, into a different nitrogen containing carboxylic acid derivative, the nitrile. Now it has to be a primary amide because we need to make a carbon to nitrogen triple bond, and so there can't have been other things on the nitrogen, or there wouldn't be room on the nitrogen to make a triple bond to the one carbon. So this is not a redox reaction. This is simply a dehydration, and it's pretty obvious when we look at the pictures. And we're going to lose the elements of water. And so then the next question is, okay, how do we accomplish this? And sometimes, you think you can do dehydration just by heating something up, and that works okay with food, but not so well with a lot of organic compounds. And so what we need is something that will take out the elements of water. And, I've worded that very carefully. We don't necessarily need to push out a water molecule per se. We just need to get out two hydrogens and an oxygen. And to get those things tied up with other elements is fine. It's still accomplishing that goal. And so one of the things that's very popular to use is thionyl chloride. Now I can warn you that one of the things that will bother you about this is what you've used that compound for in the past is in the alcohol chapter. We used it to put a chlorine in place of an OH group. And actually that was introduced back in chapter 10 when we were talking about alkyl halides. And so we learned that we could make alkyl halides from alcohols with thionyl chloride. We reviewed that again in the alcohol chapter. And something else we will see in the next chapter is how to use thionyl chloride to make acids into acyl halides. So this is a different use for thionyl chloride than other uses that you've seen, but because it's very reactive and soaks up water molecules, and so you have to be careful when you store it to keep water out of it, it's a good dehydrating agent. Some other things can be used. We also in chapter 17 learned about phosphorus oxychloride. It can be used to remove water. Or phosphorus pentoxide is very popular as a dehydrating agent. It's a little more sensitive to moisture even than the thionyl chloride, so you have to take care when you store it to keep it dry. So here's an example of what we're looking at. So when we talk about the degree of an amide, it's like the degree of nitrogen compounds, which we talked about a little bit in chapter 19. So if you think about ammonia, remember that ammonia was kind of the parent when we were discussing degrees of nitrogen. So if one hydrogen is missing from ammonia, that's a primary nitrogen compound, and when that nitrogen is directly attached to a carbonyl, then it specifically is a primary amide. If the first thing attached to the nitrogen is not a carbonyl, then it would just be a primary amine. So that's the only difference between primary amines and primary amides, is whether this is a carbonyl or not. Alright, so this is our primary amide. This is the kind of compound we need. We're going to dehydrate, in this example, with thionyl chloride, and they heat it up some. And benzene is just playing the role of solvent here. And actually, we would probably these days even use some other solvent. And so this carbon and this nitrogen stay together, and we're going to lose the elements of water out of here. And so those other two bonds on the carbon that were to oxygen and on the nitrogen that were to hydrogen, those are both gone, and we get this triple bond between the carbon and the nitrogen. And what happens to the oxygen is it ends up as part of an SO2 molecule, and the two hydrogens become part of two HCl's, which is kind of what happened to the OHs when we did the thionyl chloride on alcohols to turn them into alkyl halides. We got SO2 and one HCl out of that. Okay, so in terms of reactions of nitriles, something else that you'll hear more about in the context of chapter 21 is not only are we interested in can we make the derivative directly from the parent carboxylic acid, we are also interested in, okay, if we have a carboxylic acid derivative, can we see hydrolysis of that derivative back to the parent carboxylic acid? And the answer is yes, we can in fact see hydrolysis of all of the carboxylic acid derivatives back to the parent acid. And that is true, of course, for nitriles. And we've actually already seen that. We saw it when we were talking about halohydrin formation in the aldehydes and ketones chapter 19, that one reason people were interested in cyanohydrins is because you could hydrolyze the nitrile to a carboxylic acid. And it turns out that you can do that hydrolysis in either aqueous acid or in aqueous base. The difference is just what do you have to do when you get done. Because you're creating a carboxylic acid, if you were doing this in base, then you'd have the salt of the acid, and you'd have to do a pH adjustment. But otherwise, it's just fine to do this in either aqueous acid or base. And if you have a way to monitor the reaction, take samples out and check to see how your reaction is progressing, then you can actually stop at the primary amide, which is intermediate along the way. And remember, we just talked about making a nitrile from a primary amide, and so it turns out that you could go from a nitrile, stop at a primary amide, or if you allow the reaction to keep proceeding, it can keep going and hydrolyze all the way back to a parent acid. And so here's an example. If we have this very simple nitrile, and we put in some aqueous acid and we heat it up for a while, it could be, for an hour or two. If you're monitoring the reaction, you may be able to get a pretty good yield of the primary amide, or you let it keep going and you can make the free carboxylic acid. And your other product that's going to come out of here is the ammonium salt. So like if this was hydrochloric acid specifically, then you'd have ammonium chloride as your other product. Another interesting reaction that nitriles can be useful for, and again, I referred to this in chapter 19 when we talked about the cyanohydrins again. We can take nitriles and we can reduce those to amines. And because the nitrile carbon is at the end of the chain, then the amine that we're going to make will also be primary. So it's a primary amine, and it's attached to a primary carbon. And so that's reduction. It's a little bit more challenging or harder reduction than if you were talking about an aldehyde or a ketone, because remember that the carbon of the nitrile is at the same redox level as that of a carboxylic acid. So we're going to need to use our stronger reducing agents like lithium aluminum hydride. And so the product is going to be an amine, and you will have gone through 2 levels of reduction. Now, remember that things whose name is blah blah hydride deliver hydrides, and so when this guy, lithium aluminum hydride, delivers a hydride, it's attracted to the positive character of the carbon because of the electronegativity difference, and the nitrogen is then going to become complexed with the aluminum stuff. And so at the first part, you get this thing, which is an imine salt. An imine is similar to an aldehyde. And remember that aldehydes would also reduce with lithium aluminum hydride because you had to get them going. And so when we talked about reducing esters, for example, you could reduce an ester with lithium aluminum hydride. It would go by way of an aldehyde, but it wouldn't stop. It would go all the way to an alcohol. So this one's the same thing. It's going to go again. So this carbon still has positive character, and this negative charge isn't really that obvious because of the complex here that it's making with this salt. And so another hydride can react with this positive character carbon, put the electrons over here, and now you have even more aluminum stuff complexing with that nitrogen. And so you've added 2 sets of electrons and the 2 hydrogens, the hydrides, to this same carbon. And now when you put in some water, it just gets rid of this salt stuff, and these guys pick up 2 protons from the solution, and you get your amine. And so you can make a primary amine attached to a primary carbon from the nitrile. And this is a very nice way to get into amines. Remember that our source of our carbon in this molecule might have been an inorganic source of carbon, and so now we can make an amine from that same carbon. A really interesting thing about nitriles is that they can participate in Grignard reactions. So the nitrile carbon has a lot of positive character, as I've indicated on this drawing, and it's kind of like a carbonyl in that sense. And so a Grignard carbon will be attracted to the nitrile carbon. Of course, the electrons go out onto the nitrogen, and it makes a salt with the magnesium, kind of like it had with the aluminum. This is a kind of an amine salt. But this stuff is actually going to precipitate out, and that's what the down arrow here is for. This stuff precipitates out of solution, and it doesn't react again. Unlike, if we go back to here, this guy is actually still in solution, and so another hydride will react with it. Well, this guy precipitates out, and so it can't react any further. And so then what? So then we put in the aqueous acid, as we typically do after a Grignard. Well, then that protonates this imine, and it turns out that imines are hydrolyzed by water to a carbonyl compound. So if we started out with a nitrile, we can add one chunk of carbon to that same carbon, and we actually end up with ketones. And this is very powerful because actually all three of these groups of carbon, whoever this R is, the carbonyl carbon and this other chunk of carbon, could have come from three different places. So let's think about that in terms of an actual example. Suppose that we have this molecule, and we want to make this guy. And we might have some other ideas, but we want to try out this new route that we've just seen. And so the first question is, which one of these carbons would have come from a nitrile? And so what we just discussed is it's the carbonyl carbon. All right, so if you think about that, then we need to know how to make a nitrile. And one of the ways that we could have made a nitrile is with an SN2 reaction. And we do see that right next to the carbonyl is a carbon that could have been a primary carbon before it got attached to the nitrile carbon. So we could have done an SN2 reaction and made a nitrile out of this, and then done a Grignard with this piece. So let's see how that looks. So I highlighted in red the carbon that would have come from the carbonyl. So so we're having considered, you know, the possibility of using an SN2 reaction, then that's going to kind of dictate how we would do this. So I'm saying we're going to make this bond in the course of the Grignard. So this is the Grignard that we need, this stuff right here, and we need this nitrile. So now we have to see where did that come from, and that would have come from an alkyl halide with KCN. So we have 1, 2, 3 sources of carbon to get to this. Now if this was a synthesis problem in, say, homework, and we were starting with alcohols, you would have to show how to make this molecule from an alcohol, and you'd also have to show how to make this from an alcohol, but this is probably enough for these purposes. So what is your job? For this chapter, you need to know both IUPAC and common nomenclature, and we've talked about both carboxylic acids and nitriles, and there were a lot of common names for carboxylic acids. Some of them have only one carboxylic acid functional group, but there are also some common names for some molecules that contain 2 carboxylic acid functional groups. So you need to know all of those. And you need to be able to figure out the acid trends in a series of molecules, which is the most or the least acidic molecule in a family. And remember, that's related to electron withdrawing groups and electronegativity effects near the carboxylic acid group. And then you also need to know how to make carboxylic acids. And so we've talked about a number of things earlier in the chapter, such as oxidizing alkenes or aldehydes or alcohols, and then hydrolyzing nitriles or the Grignard reaction to make carboxylic acids. And then we've also talked about the preparations of nitriles by either making cyanohydrins or SN2 reactions, or the dehydration of primary amides, and then also the reactions of nitriles, which were hydrolysis back to the parent acid, and the Grignard reaction, or reduction to primary amines. So you need to know all of those reactions and preparations of those two groups. And we will be talking a little bit more about nitriles and obviously the derivatives, other derivatives of carboxylic acids in Chapter 21. And that concludes this section of material.